Okay, this is tutorial 7. I'm sorry. This is tutorial 6 on work and energy. My bad. Okay, I'm going to share my screen. Okay. Okay, hopefully you're seeing my screen right now. As I mentioned in class, this tutorial isn't really a tutorial. A tutorial is supposed to make you cry, push you up against your misconceptions, and force you to confront the parts of your knowledge that just aren't jiving with the world around you. And this is more just a worksheet where you practice the ideas of energy and work. And so in that sense, it's a little disappointing. So one of the most important equations in all of physics is this equation here, the Grant-High work energy equation. And it essentially says that the energy in the morning is always equal to the energy at night, except when it isn't. And it usually isn't. And it isn't when some external agent does work. We call it Verk, but it's actually physics work on the system. Now, there's also another term in here, which is heat, and they deal with that over in the chemistry department. And so we're going to let them deal with that, and we're just going to worry about external Verk on our system. And we found 3 different kinds of energy that we are going to talk about. We've got kinetic energy, which is given by 1/2 mv squared. We have gravitational energy, which is given by mgh. And we have the spring energy that we didn't quite get to in lecture, but I hope that your TA has mentioned that it's 1/2 k delta S squared, where k is the spring constant for the system. That just tells you how tight the spring is, or how stiff the spring is. We find that springs push with a force that is proportional, that's the proportionality constant, to how much they are stretched or compressed. And there's a minus sign in here, if this is a vector equation, that we usually ignore, and that's because it just gets in the way. You've got so many minus signs that one more isn't going to help you any. What this minus sign tells me is that if I stretch the spring down, it's going to pull up, and your gut knows that. So the first little exercise that we're going to do is we're going to hold this block in place on a table, and this is a frictionless table, and the spring is not connected to the block. I mean, we could take this block over here and the spring would just be sitting there. We're just pushing the block up against the spring to compress the spring. The spring has spring constant of 4,500 newtons for each meter. Now, what that means is that if I wanted to compress this spring by 1 meter, I would have to push with 4,500 newtons. So it's a fairly stiff spring. We're compressing it by a distance of 2 meters from its equilibrium length, and the block has a mass of 20 kilograms. Of course, the table is frictionless. Now the hand releases the block and it is launched across the table to point A, and point A is at some point beyond where the spring is still touching the block. So if we ask what kinds of energy does the block, spring, earth system have before the hand is released, well, it's going to have spring energy. And that's the 1/2 times the spring constant of 4,500 newtons for each meter times the compression of 2 meters squared. And that's just going to give me 9,000 joules. Okay. And if we draw a free body diagram for the block at an instant in time while it's still being pushed by the spring, but the hand has released the block, we've got weight down, earth acting on the block. We have the table pushing with a normal force on the block. And we have this force, it's also a normal force by the spring on the block. Now, we're asked to consider the block earth spring system. And the question is, which of the forces, if any, on our diagram are exerted by objects external to the block earth spring system? Well, this is the earth on the block, and that's one part of my system, the earth, on another part of my system, the block. This is the spring on the block. Again, that's one part of my system on another part of my system. So it's only this one that is an external force, because the table is not part of my system. But if I ask which of the forces, and the key phrase is if any, do external work on the block earth spring system, the answer is none. And that's because this normal force, which is the only external force by the table on the block, is perpendicular to the motion. And so we have Verk external is equal to 0. Now, as the block is being pushed by the spring does positive work on the block. Why does this work not change the energy of the block earth spring system? And that's because it's only external Verk can change the energy of the system. Okay. Now, this turns out to be a very useful way of solving problems, because the work done by this push by the spring is complicated. It's complicated because the spring is sometimes pushing very hard when it's compressed a lot, and it's sometimes pushing not so hard when it's not very compressed. And so if we wanted to figure out the Verk done by this normal force by the spring, we would have to use calculus, and it would be messy. But if we instead talk about the energy stored in the spring, then it's only external Verk that can change that energy. Well, let's go to page 2 here. When the block gets to point A here, it's moving, but it's no longer touching the spring is no longer compressed. And so at this point, all we have is kinetic energy, or 1/2 mv squared. If we use the work energy equation to find the speed of the block when it reaches point A, we would say energy initial is equal to energy final, except when it's not. But we just said that the table does no external Verk because it pushes perpendicular and it's frictionless. And so that means that my potential energy spring initial is the only kind of energy I started with, has to equal my kinetic energy final. Well, that means that 1/2 K delta S squared is equal to 1/2 mv final squared. Well, we said that this potential energy here was 9,000 joules, and that's going to be equal to 1/2 times the mass of the block was 20 kilograms, and V final squared. Now, if I solve for that, I'm going to get 900 meters squared seconds squared is equal to V final squared, and that gives me V final is 30 meters per second. Notice that your answer did not depend on how far A was from the initial position of the block, as long as it was past the equilibrium position of the spring. Why is this true? Because it was a frictionless table. Because Verk external was equal to 0 on the frictionless table. Could we have used Newton's laws and the kinematic equations to solve this problem? Well, no. And that's because if we had done that, we would have had to we would have to find the acceleration of the block, and because the normal by the spring on the block varied, so would A. And remember, we can only use those kinematic equations for constant acceleration. Now, suppose that the table in question was the Ugly Giants table that we encountered earlier in the course. Remember, that table was 80 meters tall, and the block slides past point A and off the edge of the table onto the floor. We wish to find the speed of the block at point B just before it hits the floor. Well, we've already solved this problem with the kinematic equations. This was our first projectile motion problem, and we found that this thing was going 50 meters per second right before it hit the ground. And we even found that the angle at which it was traveling. But now we're going to do the same thing with energy. The work energy equation relates the energy at a later time, that would be this later time, to the energy at an earlier time, that would be this earlier time up there. and the work done on the system between those two times. Now, remember, it's a frictionless table, and we ignore air resistance, so we don't have to worry about the work done by that. We do not actually have to know when these times were, just that it was happening at what was happening at those times. We choose our initial and final times to be either events we know about or events we want to know about. In this example, we will choose the initial event to occur when the block passes point A, and the final event to be just before the block hits the floor, which we'll call point B. So it'll be point B and be point A. What kinds of energy does the block Earth spring system have when the block passes point A? Well, it's moving, so it has kinetic energy, and it's up off the floor, so it has gravitational energy. So this is a little bit different than on the first page. On the first page, we assumed that this tabletop was our height 0, and then we find out that, whoa, man, it's actually an 80-meter tall table. That's quite a tall table. And so we have to redefine our 0, and that brings in this gravitational potential energy. If we draw a free body diagram for the block at an instant in time while it's falling towards the floor, well, we remember from our study of projectile motion that anything in free fall has a simple free body diagram. It only has one force acting on it, and that's the gravitational force towards the center of the Earth. And since that is part of our system, the Earth acting on another part of our system, the block, we have no external forces. Ooh, there's an N in there. Okay, let's just spell it correctly. External forces. Okay. Now, we are then asked, what kinds of energy does the block Earth spring system have when the block reaches point B? Well, there it's only kinetic energy. And that's because we define the floor as our 0 of height. So if we use the work energy equation to find the speed of the block when it reaches point B, we say initial energy is equal to final energy, except when it's not. But in this case, we said that it is, because there's no external Verk. Initially, we had kinetic energy initial, and we had gravitational energy, and then at the end, we only had kinetic energy. So we've got 1/2 mv initial squared plus mgh is equal to 1/2 mv final squared. And we can cancel out the mass because it's in every term. And what we get is V final is equal to the square root of V initial squared plus 2gh. And that's going to be the square root of 30 meters per second. We've got to square that. Plus 2 times g is 10 meters per second squared times the height of 80 meters. And if I work that out, what I get is the answer we got before with our kinematic equations of 50 meters per second. What's missing is that we found in our kinematic approach that this thing was heading in a direction of 53 degrees below the horizontal, with an x part of the velocity that was 30 meters per second and a y part that was 40 meters per second. And that's what gave us the 50 meters per second here. Could we have used Newton's laws in the kinematic equations? Yes, we did. Okay. Now choose your initial time to be when the block is held by the hand against the compressed spring. Solve again for the speed of the block at point B. Well, if I do that, I start again with my energy initial is equal to energy final, and except when it's not. But in this case, it was a frictionless table all the way along, and the spring was part of our system, and the table pushed perpendicular to the motion. So again, there was no work done. But now it was spring energy and gravitational energy initially, and it was kinetic energy final. Well, that just gives me 1/2 k delta S squared plus mgh is equal to 1/2 mv final squared. If I plug this in, I get V final is equal to the square root of k over m delta S squared plus 2gh. And when I plug everything in, I get 50 meters per second again. Now that shouldn't surprise us, because here we've got the same mgh that we had up here. And we found that the spring energy of 9,000 joules was just turned into kinetic energy when it got to point A. And so you've got the same amount of total energy on the left-hand side of the equal sign, whether it was spring energy and gravitational potential, or whether it was kinetic energy and gravitational potential. We get the same answer. Now we're going to suppose that the block has to slide across a rough patch on the table of length 30 meters that has a coefficient of kinetic friction of 0.4. We again wish to find the speed of the block when it reaches point B. Since we do not know or not told if point A lies before or after the rough patch, let us again choose our initial time to be when the hand is holding the block. So, is the frictional force an internal force or an external force? Well, that's an external force, because it's exerted by the table on the block. And this is going to bleed energy out of our system. So the work done is going to be negative the friction by the table on the block times the distance. Well, the friction is going to be mu sub k times the normal force by the table on the block, and times the distance. Now, the mu sub k, we were told, was 0.4. The normal if we draw a free body diagram, we have a weight force that is 200 newtons, just M times G. We have a normal force by the table on the block, and we have this friction by the table on the block. Well, there's no acceleration up or down, and so this has to be 200 newtons. And so I put that in here, and the distance was 30 meters. And what we end up with here is a negative 2,400 joules. If we use the work energy equation to find the speed of the block when it reaches point B, what we have is energy initial plus Verk external is equal to energy final. Well, this is going to be, let's do it when the spring is compressed. So we would have mgh for gravitational potential plus 1/2 k delta S squared for the spring energy. We would have the Verk external, which turns out to be a negative value. And then finally, we would have the final kinetic energy. Now, it turns out that this value here, mgh, is just 16,000 joules. And we said that this was 9,000 joules. And the Verk, we said, was negative 2,400 joules. And that's equal to 1/2 times the mass of 20 kilograms times the V final squared. Now, if I find V final, well, 16,000 and 9,000 is 25,000. And then I've got to subtract off the 2,400 and divide by 10. And kilograms. And then what I get is 47.5 meters per second. And let's see. Yeah, that looks right. Okay. Now, this last page is just an old exam question. We have this block of mass 1/2 kilogram released from rest at this point A, which is 20 meters above what we're calling the floor, or height 0. The block slides down a track around a loop-to-loop of radius 7.5 meters and back up another track. There's no friction on, the track. So the mechanical energy of the block Earth system is just going to be the gravitational potential energy at A, and that's just equal to mgh at A, and that's going to be 1/2 kilogram times 10 newtons for each, well, let's call it, newtons for each kilogram, and then 20 meters. The kilograms cancel and we get Newton meters or joules. and that's going to be 100 joules. Find the work done by the track. The Verk external is 0, and the reasoning is that the normal by the track on the block is perpendicular to the displacement at all times. What is the speed of the block at point A? Well, here we would use energy, E initial plus Verk external is equal to E final, and there's no external Verk, we said. So we have 100 joules initially, and that's going to equal 1/2 times, at B, I only have kinetic energy, and that's going to be 1/2 times 0.5 kilograms times V final squared. And that's going to give me a V final of 20 meters per second. If the block were released from point D instead of point A, would any of your answers to part A change? No, it's still going from 20 meters down to the floor, and so no change. Now, when it goes around the loop, if we want the speed at point C, right here, well, if we use energy, and use the fact that there's no external Verk, then we have here, we started with 100 joules, and then at point C, we have gravitational energy, and that's going to be M times G times H, and that's going to be 15 meters. And then we have kinetic energy, where that's, I'm sorry, 1/2 kilogram times V final squared. And you see that that's just algebra. So this is going to give me 100 joules. This is going to give me 75 joules is equal to V final squared. And I've got to divide by 1/2 kilogram, or 0.25 kilograms. And that is going to give me a V final of 10 meters per second. Okay. What is the acceleration of the block at point C? Well, that is just given by V squared over R. So that's going to be 10 meters per second. I've got to square that and divide by the radius of 7.5 meters. And that's going to give me 13.3 meters per second squared. And it's down towards the center of the circle. If we draw a free body diagram for the block up there, we have a weight force, Earth on the block. And for 1/2 kilogram, that's just going to be 5 newtons. We have a normal force by the track on the block. And we can find that normal force by saying that, let's call down the positive direction. If we say F net equals MA, well, I have the normal by the track on the block, and it's in the positive direction, what I'm calling the positive direction. And I have the 5 newtons due to the pull of the earth, the gravitational force we call weight, and that's equal to the mass of the block times its acceleration, which would be in the positive direction of 13.3 meters per second squared. And if we solve that for the normal force, what we get is 1.67 newtons. And so you see that I've drawn my free body diagram poorly. The normal force should be smaller than the it should be smaller than the weight force. And that is the tutorial number 6. And now I'm just going to close this off. Stop the share, stop the recording.